Today we're going to talk about calculating electrical potential of half cells. And that's a very important concept because we're going to see in our video today, we're going to actually see how we can do that calculation. It's very important that you learn how to do this because you could use this in calculating the battery's potential for your laptop that's in front of you. Okay, what is this potential that's caused in an electrochemical cell? Where does it come from? So this potential is the ability of it to produce a current. So if we look right here, we see that that's the most important part. We want to get electric current from our voltaic cell, and we need to somehow figure it out what that potential is, and we're going to figure that out in volts. So if you ever looked at a battery, you might have saw that it was 1.5 volts. Or a car battery is like 12 volts. All right? So we use volts as a way of looking at electric potential. Current, on the other hand, is measured in amperes, and in physics you'll learn how to relate the two. Okay, we can't just take and measure a half cell. It's impossible to measure just one half cell. So we've looked at the zinc half cell with the copper half cell, for instance. There is a way of determining the potential of the whole cell if we know the half cell measurement. So we have to have some sort of standard, and that's what we're going to do first. We're going to learn how to find out something that's our standard half cell, and then everything else's measurement is related to that. And we're going to talk about one of the half cells having a greater tendency to acquire electrons, so that tends to be reduced, and the other one is going to be oxidized. Okay, so they're competing for the electrons, so there's a difference in it, and one's going to receive the electrons and one is going to give up the electrons, and therefore a potential is created. Okay, we usually measure these as reductions. So usually we're going to look at the tendency of something to be reduced. So if we think of reductions, we could think of the copper 2 plus 2 electrons going to copper metal that we saw in the previous lesson. Okay, so they're always going to be in this form for reduction potential. And the one of the half cells that follow this pattern is basically what we're going to say is reduction. And we saw that in the other half cell we had zinc going to zinc 2 plus and 2 electrons. Okay, so that was what we saw previously. Now, once we have those two terms, we have a simple equation. Okay, we basically can find the complete voltage of the cell by taking the reduction potential and subtracting the reduction potential of the oxidized component. So this is the species that's reduced, and then we take the same number from a chart and we subtract it, and that's how we can find the potential of the cell. Now this becomes very important. Okay, usually we have something called the standard potential. Anytime we have something that we call standard, we write this little 0 here. So what does that mean? That means that the temperature is approximately 25 degrees C, 101 kilopascals, which is basically 1 atmosphere. And the solution that the metal is put in is 1 molar. Okay? So that makes it a standard cell potential with these conditions. So this is usually sea level. This is what we typically think of as room temperature. And this is a 1 molar solution in each of the half cells of the salt of the half cells, or acid. Okay, now how do we get these numbers? Well, we had to have a standard, and our standard is a hydrogen electrode, and we actually assign, okay, the value is assigned, it's not calculated. So we say that whatever hydrogen is doing at the electrode, we're going to give it a value of 0. So some things will have a E greater than 0, and some things will have an E less than 0. So in other words, in these cases, if it's above, okay, it's more likely to be reduced, we're going to see. Okay, so it's a little bit different in what we learned in the last thing where we had the oxidation on the top. Okay, so let's continue talking about the standard hydrogen electrode. Okay, they kind of wanted to trick you a little bit here and say it's 24 degrees, it's really 25 degrees. Okay, we have a hydrogen concentration of 1 molar because we have acid solution, and we have hydrogen gas at 1 atmosphere, 101 kilopascals. So hydrogen is a gas, so somehow our electrode is a platinum wire, and then we bubble hydrogen on it. So we need something to take those electrons and allow them to flow through the wire. So the gas comes in here, it bubbles right here, and then we can have basically our reduction or our oxidation occurring here at the electrode. So it depends on what we connect this to, if it will be reduction or oxidation. So if we write this as a reduction equation, that would be hydrogen in the it would be hydrogen in the solution right here is going to come up and take 2 electrons and then form hydrogen gas, and it will bubble. So this is turning this acid solution into more hydrogen gas. Okay? And we set that as 0. Since we have double arrows here, that's equilibrium, so it's reversible. And as I said before, if it becomes a reduction like this, or if it's actually an oxidation, it depends on what it's connected to. Okay. I'm going to here stop the tape for a second, or actually give you a question on Educanon, and you should know this answer from the previous slides. That's right. It's assign a value of 0 volts. Notice we also use the E0 because it's a standard reduction, meaning that it's at standard temperature, pressure, and concentration. That's what the little 0 means right here.